This is a video on finding the error bound for Taylor polynomials. The question states, use Taylor's theorem to find an upper bound for the error in the approximation sine of 0.2 equals 0.2 to the first over 1 factorial minus 0.2 cubed over 3 factorial plus 0.2 to the fifth over 5 factorial. So let's first recall Taylor's error theorem. And what it says is that the remainder after taking the nth degree Taylor polynomial evaluated at a number x is equal to the n plus first derivative evaluated at some number between x and c divided by n plus 1 factorial times x minus c to the n plus 1. One of the tough parts about this is to try and figure out what all of this means. So let's look at this one at a time. So first, we're looking at a Taylor polynomial for the sine, and we can think of this as a sine of x is x to the first over 1 factorial minus x cubed over 3 factorial plus x to the fifth over 5 factorial. And we see that we have a fifth degree polynomial. So that means n is equal to 5 here. Next, notice that it's just x to the first and x cubed and x to the fifth. It's not x minus a number, so that's just x minus 0. So c equals 0. The function is sine of x. So f of x equals sine of x. And we need the n plus first derivative. N is 5, so we need the sixth derivative of our function f. So the first derivative is cosine of x. The second derivative is negative the sine of x. And then we can continue taking derivatives, and I'll let you think about that and work that out. And what I got when I took the sixth derivative of f of x was negative the sine of x. We want the sixth derivative evaluated at this mysterious z that is somewhere between x, which is 0.2, and c, which is 0. One nice thing about the sine of x, it doesn't matter what we're plugging in. We always get something between negative 1 and 1. And when we take an absolute value, we can say that the sixth derivative is always less than or equal to 1 in absolute values. So in particular, I can take this f super n plus 1 of z, and I can replace it with a 1. One more thing. Our x was 0.2, so that's what we're plugging in for our x here at x minus c, and here at r sub n of x. So let's put this all together. I can say that r sub n of 0.2, that was x, is less than, I replace the f super n plus 1, or the sixth derivative at z, with a 1, over 6 factorial, because n was 5, n plus 1 is 6, times 0.2 minus c is 0, so minus 0, to the n plus 1, which is 5 plus 1, or 6th power. At this point, I just put this in a calculator, and what I got was that the remainder was less than 0.000000089. So we could see that the remainder, the error bound, in using Taylor's theorem, is very, 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 very small. And I'm done with the problem.